In this video, I'm going to be introducing one of the most important techniques in mathematics, something known as differentiation. We'll start by understanding what differentiation really is, and then we'll learn a simple rule to find the gradient of a curve at any point. By the end of this video, you'll be able to explain what differentiation is and why it's a useful tool. You'll understand that differentiation finds the gradient function, which gives the slope, the gradient of a curve at any point. You'll also recognise and use the notation for the derivative and apply the power rule to differentiate polynomials and other functions. Okay, so let's get started. Before we dive in, let's think about why this idea of differentiation or rate of change is so important, so crucial to understand. In almost every field, it's not enough to know just the value of something. We also need to know how fast it's changing and whether it's increasing or decreasing. If you think about business, it's great to have high sales, but it's even more useful to know if those sales are accelerating or slowing down, if they are increasing or decreasing. In epidemiology, knowing the number of cases of a disease is important, but knowing the rate at which they are spreading helps us to predict and control an outbreak. This concept, finding the rate of change at an instant, is exactly what differentiation is all about. In physics, the rate at which distance is changing is something that we talk about quite regularly. It's called speed. The rate at which velocity is changing is called acceleration. So this idea of rate of change is a cornerstone of physics and many other fields. So how do we measure the rate of change? For a straight line, we find the gradient using rise over run. This is something that you should have used before. Also, this can be stated as being change in y divided by change in x. And in mathematics, we often use the Greek letter delta, which looks like a triangle, to represent change. So delta y over delta x means change in y over change in x. And we've used that many times before to work out gradient. But for a curve, the gradient is different at every point. You can find the average rate of change between 2 points, but what we really want is the rate of change at a specific single moment in time. We imagine making the change in x and the change in y infinitesimally small, almost zero. And what you can see is that when you make the change in x and the change in y infinitely small, you essentially create a tangent line to work out the gradient at one specific point in time. When that change in y and change in x becomes infinitely small, we use a different notation. Rather than using delta y over delta x, we write dy over dx. And the way we read that is we say dy by dx. So that is the notation that is always used for the derivative, the result that we get for the gradient function. Now that we know what differentiation is and how to talk about it, we need to find a pattern, an algebraic way that we can find the derivative, that we can differentiate a polynomial. Now there is a way of doing this more rigorously than I'm going to show, which is a method using what's called first principles. We're instead going to look at it by trying to spot patterns by collecting some data for linear, quadratic, cubic and quartic functions. So we'll look at each of these in turn and hopefully then we'll be able to spot what the pattern is. So if we start with the graph of y equals x, which is a linear function, as we move a point across from x is minus 2 to x is minus 1, x is 0, x is 1, x is 2, we can see, unsurprisingly, that the gradient stays the same. The gradient is 1 over 1, which is just 1 every single time. So for our linear function, the gradient is always equal to 1 no matter what the x value is. So what we can say is that if y is equal to x, dy by dx is going to be equal to 1 because the gradient is always equal to 1. If we move on to a quadratic function, y equals x squared, again we can take gradients for different values, but now it's a curve, which means that the gradient is going to change for different values of x. So if we now collect some data, some different gradient values for the different x coordinates, for example, we can see that when x is minus 3, the gradient is minus 6. We can see that when x is minus 2, the gradient is minus 4. So if we collect all of those different x values and gradients, hopefully we can start to spot a pattern that's going on. If we look at it in a table, you should be able to see that the x coordinate is always getting doubled to give the gradient. What that means is that if the function is y equals x squared, the gradient function, dy by dx, is 2 multiplied to the x coordinate. Right? You take the x coordinate and times it by 2, that tells you what the gradient is going to be. So dy by dx is equal to 2x. If we then do that again with a new function, y equals x cubed, we can collect different gradients for different x values. Again, once we've done that, we can put it into a table. This time round, the formula might be a little bit trickier to spot. So if we square the x coordinate, it maybe makes it a bit easier to see what the rule is. If I take the x coordinate and square it, giving me 9, 4, 1, 0, and so on, hopefully you can see that the gradient is always 3 times by that value. So for example, 9 times by 3 is 27, 4 times by 3 is 12. And so what have we found there? We found that the gradient is always 3 times by x squared, 3x squared. So when y equals x cubed, dy by dx is 3x squared. And if we do it one more time by collecting some data from a quartic function, y equals x to the power 4, again we can take a few different x values between minus 3 and 3, work out the gradients. When we put all that data into a table, again it's initially quite difficult to see the pattern, but if we work out what the x coordinate is cubed, the pattern becomes a little bit more apparent. Because if you take the x cubed value and multiply it by 4, it gives you the gradient every single time. And so what we found is that for this function, dy by dx, the gradient function, is 4x cubed. Now if we put all of those results together in one table, hopefully we can start to see what's actually going on here. If we look at the function y equals x, the gradient function was 1. When it was y equals x squared, we had 2x. When it was y equals x cubed, we got 3x squared. And when it was x to the power 4, we got 4x cubed. What seems to be happening every single time is that the power of the function is dropping down to the front, and the power itself is going down by 1. If we look, for example, at x to the power 4, the 4 drops down to the front, and then the power goes down by 1, giving us 4x cubed. And that is the general result that enables us to differentiate any power function. If we write that in general terms using letters, it means that if we have the function x to the power n, we bring the n down to the front and the power decreases by 1, so the power becomes n minus 1. And that's the most important result for being able to differentiate a power function. You bring the power down to the front and take 1 away from the power. So although it's taken a long time for us to get there, actually to do differentiation is a relatively straightforward process. And in the next video, we'll have a look at a lot more examples of how to actually apply this technique to lots of different polynomials.